Hi, good morning, everybody. I'm going to talk to you today about 12.1 vector value functions. And we're just going to go through a whole bunch of examples. Okay, so these are called vector valued functions. Just to give you an idea of what this is, basically what it is, it's a vector function. You've got your input is the parameter. Oftentimes it's t, but it really could be anything. And the output is what you would plot, what that graph would look like in 2 dimensions or in 3 dimensions or more. Okay, so for instance, if I have a vector valued function r of t defined in 2 dimensions, and oftentimes how you'll see this, that'll be f of t in the I direction plus a g of t in the j direction if it's in 2 dimensions. So this one I'm going to do in 2 dimensions. Okay, and you can also see this in component form, which is how I will usually write this. Okay. Okay. And what happens is, let's say we're graphing a line. We've got this line in 2 dimensions. So basically what this function does, every t value is going to be an input and will get you to a different point on this curve. Okay, so this one right here would be, let's say, r of t1. Then you would have another vector, let's say, r of t2. Another vector, r of t3. Okay, in this case, I just drew a line. But basically what this vector valued function does, it's going to trace out a curve or a line, really any kind of curve, in your 2-dimensional space here. Okay, then we might have something in 3 dimensions. So you've got this curve that winds around in 3 dimensions. Okay, and you'll have this vector over here might be an r of t1 that gets you to this point on your curve. R of t2, r of t3, and so on. Okay, so for different t values, you'll get to different points on this curve. Okay, so this vector value function is going to have an x component, a y component, and a z component. Okay. And you can limit the domain if you want to graph out a certain section of the curve. Here's an example. Let's say we wanted to use a vector value function for a line segment from, let's say we're going from the point, say 0, 2, 1 to the point, let's say, actually, I'm going to do this a little differently. Let's do 2, 1, 0 to 0, 3, 5. I'm drawing it this way just to show you what this would look like. And this is in 3 dimensions. Okay. So we want to go from this point 2, 1, 0 to the point 0, 3, 5. Okay, so you're going from a point on the xy plane to a point on the yz plane. So this would be your vector value function of this line segment. Okay, and that point might look like this over here. Okay, so what we're going to do, and when we have a vector equation of a line, and we want to write it as a vector, we could write this thing in parametric equations. We could write it in symmetric equations. But then there's a third way we can write it. We can write it as a vector equation, something that looks like this. Okay, so sometimes it's easier, since this is a line, we know our x value is going to be equal to our original x, let's say x0 plus a times t. Y would equal y0 plus bt. Z would equal z0 plus ct. Okay. The reason I'm writing it this way is because we've written parametric forms of lines before, where ABT is our vector that gets us from this point to this point. So that would be 0 minus 2, 3 minus 1, 5 minus 0. Okay, so our x is going to be equal to, let's use this as our initial point, 2 minus 2t. Y is equal to 1 plus 2t. And z is going to equal 0 plus 5t. Okay, so as you can see, when t is equal to 0, we're at the point 2, 1, 0. We're right here. Now, when we've traveled this vector from here to here one time, so basically when t is 1, we're going to go from this point to this point, because basically we've added this vector one time. Okay, so when t is 1, we're going to be at 2 minus 2. Our x value is 0. When t is 1, we're going to be at 1 plus 3. That's going to get us here. When t is 1, we're going to be at 5. So this is our parametric equation of a line. The vector equation of the line, r of t, the line segment, since we only want to go from this point to this point. If we don't limit the t values, then it's a full line. Okay, but since we just want a line segment, I'm going to use the three components, 2 minus 2t, 1 plus 2t, and 5t. But now to limit to a segment, we want t to go from 0 to 1. That's going to give us the line segment from this point to this point. Okay, I'm going to go through a couple more examples. We're going to do some examples from the book. Example 1 is sketching a plane curve. Okay, so example 1 says, sketch the plane curve. This is on page 821. Okay. Sketch the plane curve where your vector equation is r of t is equal to 2 cosine t, negative 3 sine t. This is just in 2 dimensions. It's on a plane. And t goes from 0 to 2 pi. Okay, so sometimes it's helpful to rewrite this in parametric equations. You know that your x value, this represents your x, this represents your y. It's equal to 2 cosine of t. Y is equal to negative 3 sine of t. The reason we do that is sometimes it's easy to use trigonometry to figure out, to basically get this thing in terms of x and y's so we can graph the function. Okay. Noticing there's a cosine t and a sine t, we can solve this one for cosine of t, which equals x over 2. Sine of t equals negative y over 3. And we know that cosine squared t plus sine squared t, this is a common trick we're going to use in this class, especially in this chapter. So since cosine squared t plus sine squared t is always equal to 1, what we get is x over 2 squared plus negative y over 3 squared is equal to 1. Just replacing cosine t with x over 2, sine t with negative y over 3. And we get x squared over 4 plus y squared over 9 is equal to 1. And I know my t value is going to go from 0 to 2 pi. Okay, so if we sketch this, we know that this is an ellipse. In x direction, we know the center is 0. We're going to go in the x direction, we go 2. In the y direction, we go 3. And there is our equation. And I will want you to show the direction of the curve. So when t is 0, where are you? So when t is 0, we start at the point 2 cosine of 0. Cosine of 0 is 1, so we're going to be at 2. And when t is 0, our y value is going to be 0. Okay, so we're starting here. Now what happens? Let's try when t is pi over 2. Okay, so when t is pi over 2, we get 2 times cosine of pi over 2. So our x is going to be 0. Sine of pi over 2 is 1, so we're going to be this way. So our curve actually goes in this direction. Okay. So you always want to give the direction of your curve. Okay. Also on that same page, we're going to go to example 2. Example 2, okay, this is a space curve, so this is in 3 dimensions. So r of t, we want to draw this. R of t equals 4 cosine t, 4 sine t. Comma t. And it says t goes from 0 to 4 pi. Okay, so again, we're going to have x equal this thing, 4 cosine t, y is equal to 4 sine t, and z is equal to t. Okay, so z is not constant. Up here, z was constant. Z was always 0. Here, z is not constant. Z is changing. Okay, so we can look at these two together. You can again do cosine squared t plus sine squared t, which is equal to 1. But cosine t is going to be x over 4. So squaring that, x squared over 16 plus y squared over 16 is equal to 1. Okay. So this thing, well, that's a circle if you're on a plane, but we're not on a plane. So this thing here is actually in 3 dimensions. It's a circular cylinder, okay, with a radius of 4. So on the xy plane, you would have this circular cylinder. This would be at 4. And this would be at 4 also. And we've got a cylinder. Okay, now where does our curve start? Well, we start with t is 0. When t is 0, we could say r of 0 is equal to 4 times cosine of 0, which is 4, 4 sine of 0, which is 0, and then 0. So we're at, our vector would get us to the point 4, 0, 0. So we're starting right here. Now, since their x value is 4 cosine t, we could plug in, let's say, a pi over 2, just to check. But it should be traveling from the positive x to the positive y. Okay, so pi over 2, plugging that in, 4 cosine of pi over 2 is going to be, cosine of pi over 2 is 0, so we get 0. Sine of pi over 2 is 1, so we'll get 4. And then our t value is going to be pi over 2. So when theta is pi over 4, which gets us over here, notice what happens. When our angle t is pi over 4, or pi, let me say it again, pi over, when this is pi over 2, our z value is also pi over 2. So we're actually traveling around the cylinder like this. Okay? And as you can see, it's going to continue doing that. And as t goes from 0 to 4 pi, we actually make 2 full revolutions. Till we end up back basically right above here. Okay, at the point when r of 4 pi is going to equal to 4 comma 0 comma 4 pi. Okay, and our curve will go in this direction, going this way. Okay, so that's how we would sketch a curve in 3 dimensions. Now notice, this is simply a curve. For any t value, you can only be at one point. Okay, this, I didn't draw that great because this does keep rising just because of the dimensions. It kind of looks like it doesn't. Okay, it stops there. Okay, so I'm going to do another example. Now we're going to kind of do the opposite. Example 3, we're going to be given rectangular coordinates or a rectangular equation of a curve, and now we want to come up with a vector equation. Okay, so example 3, this is on the next page, page 822. We've got y equal x squared. Okay, we know that's a simple parabola. Okay, and there's no restriction. This will continue going up. But we want to come up with a vector equation. So a couple ways we can do this. Simplest way, you can just call x equal to t. And if x is t, then y you have in terms of t. And your y will be equal to t squared. So your r of t would simply be t comma t squared. Just as simple as possible. We know that x equals t and y equals t squared. Okay, that's one way to do it. If you want to make t your parameter, notice here t is the parameter, meaning you had to get x and y both in terms of t. Okay, but sometimes it's simpler, since y is already defined as a function of x, sometimes it's simpler to just say that x is my parameter. Okay, there's no reason you can't do that. You could say x is just equal to x, and we know that y is equal to x squared, so we could say our vector, our parameter, instead of being t, can just be x. R of x would equal x and x squared, where x is your parameter. You don't have to write this out that x is the parameter. I'm just doing that to show you that there's nothing that tells you that t has to be your parameter. Okay, then let's go to example 4. Okay, example 4. Sketch the space curve. So here's going to be a curve in 3 dimensions, represented by the intersection of the semi-ellipsoid, x squared over 12, plus y squared over 24, plus z squared over 4 is equal to 1. We're going to say that's the semi-ellipsoid, where z is greater than or equal to 0. So the top half of that. And then we also want the parabolic cylinder y equals x squared. So we're going to intersect these two curves, a parabolic cylinder with a semi-ellipsoid. Okay, so let's first graph this ellipsoid. So in the x direction, we're going to go square root of 12, which is somewhere between 3 and 4. 1, 2, 3, 4. Somewhere around there. Y value, we're going to go square root of 24, which is a little bit more than, almost 5, a little less than 5. Okay, and then the z, we're only going to go up to 2 and down to -2. Okay, so you've got this thing here. So basically, we've got this, and we're just going to do this thing. We just want the top half of this thing. Okay, so we've got this thing that goes up and around here, almost like a loaf of bread, maybe. Okay, and then on top of this, we're going to draw this thing. We know that this thing in the xy plane looks like this. It opens up towards the positive y. So that's going to go this way. But it's a cylinder, so it kind of goes this way. So this thing's going to cut through here. So where does this cylinder cut through this loaf of bread? Well, it's going to hit the top here. And from here, it just kind of comes down to here, around here, on the other side, it kind of comes down, comes back on the other side. Okay. Okay, so this is your curve. Okay, if you can picture that, that's running along the top of your loaf of bread, but it's also on this parabolic cylinder. Okay. All right, so what we have here, right here, this is our curve of intersection. Now we want to come up with an equation for that curve, okay? So we know that we've got a y has to equal x squared for every point on this curve. We know the curve's only going to go from here to here because we want it along the top half, okay, not along the bottom half, because z has to be greater than 0. Okay, because so there are going to be some limitations on our parameter. So let's first write this out. We could simply say x is equal to x. We could say y is equal to x squared. You know, those two things have to be true, but then we also know this has to be satisfied. So solving this thing for z, we're going to have z squared over 4 equals 1 minus x squared over 12 minus y squared over 24. Multiplying both sides by 4, z squared is equal to 4 minus, multiply by 4, x squared over 3 minus y squared over 6. Okay, z squared is going to be equal to this thing. Okay, so let's get common denominators here. So we could put everything over try putting everything over 12. So that would be 48 over 12 minus 4x squared over 12 minus 2. Oh, okay. We've got to get our, okay, minus 2y squared over 12. So z squared is equal to 48 minus 4x squared minus 2y squared all over 12. Okay, so, but we want z in terms of just one parameter. We don't want two parameters here. We only want one. So we have to get rid of that y squared. So we have z squared is equal to 48 minus 4x squared minus 2 and y squared. Well, y is equal to x squared. So we plug in an x squared there and then square it. We're going to have 2x to the 4th all over 12. Okay. And we can reduce this by 1, can't we? So this is now going to be z squared equals 24 minus 2x squared minus x to the 4th over 6. Yeah, I could have gotten these to be 6s instead of, I needed them to be 12s because of that. Okay, so this thing, let's solve for z. Z is going to equal plus or minus the square root of all this, 24 minus 2x squared minus x to the 4th over 6. Okay, now plus or minus, we actually want this to be plus because we know z is greater than 0. So our z value is simply equal to the square root of 24 minus 2x squared minus x to the 4th over 6. And I think we can factor that. And the reason we want to factor that is because it's going to be a little easier to come up with our domain for this function. Okay, so let's do minus plus x squared and minus x squared because we know to get this at the end. These may be 6 and 4. I think 6 and 4 works. Maybe 6 here and 4 here. Let's double check that. So that's going to be 24 minus 6x squared plus 4x squared. That works. Okay, so their z value is going to be square root 6 plus x squared times 4 minus x squared all over 6. Okay, so that's going to be these are our parametric equations, which you can turn into a vector equation. X comma x squared comma square root of 6 plus x squared, 4 minus x squared, and 6. Or if you don't like using x's as your parameter, you can use t as your parameter. So t squared, square root of 6 plus t squared, and 4 minus t squared over 6. Okay, now we can limit our t value. We know that we cannot have a negative under the radical. Okay, so we want to know where this function actually exists, where this function is continuous. And this thing under the radical is going to be negative anytime your 4 minus t squared is less than 0. So we want it to be positive. We want it to be greater than or equal to 0. So we need 4 greater than or equal to t squared. And that happens when t is between negative 2 and 2. So we've got t between negative 2 and positive 2. Okay. So we can limit our parameter to that. Okay. And now, since we kind of led into it, let's talk about limits and continuity a little bit. Okay. When you're finding a limit of a vector valued function, okay, it's pretty much the same as finding a limit of any function. You just have to find a limit of each of the 3 components separately. Okay. And then when you want to find where something is continuous, you're going to find basically where it's defined and use the regular rules of continuity to figure that out. Okay, so let's talk about, and now we're going to page 823. We're talking about limits and continuity of vector value functions. Page 823. Okay, the definition of a limit of a vector valued function. I'm just going to define it when we've got a space curve. So if R is a vector value function such that R of t is equal to, we've got 3 components. So we've got a f of t, that's a vector, so we make that, g of t, and h of t. Then the limit of R of t as t approaches a is equal to, we just take 3 separate limits. The limit as t approaches a of f of t, the limit as t approaches a of g of t, and the limit as t approaches a of h of t. Okay, and a limit of a vector value function will exist, or I shouldn't say that. What I want to say is a vector value function is continuous. So R of t is continuous, let's say at t equals a, if the limit of R of t as t approaches a is equal to the value of R of a. Okay, so you're not only approaching the same value from both sides, that value also has to exist in order for this to be continuous. Okay, so we'll just do a couple examples. Example 5. This is on page 824. Okay, so discuss the continuity of the vector value function R of t equals t comma a squared minus t squared at t equals 0. Okay, so is this function continuous? Well, let's first find R of 0. The vector R of 0 would be 0 comma a squared minus 0. Okay, now let's find the limit, because we need to know that R of a, R at that value, is equal to the limit as t approaches that value. So it's the limit as t approaches 0 of our function a squared minus t squared. So you're taking the limit as t approaches 0 of each of these things. And the limit here is going to just be 0. The limit here, t approaches 0 of a, is just a. And the limit as t approaches 0 of a squared minus t squared is a squared. Okay, these match. So therefore, R of t is continuous at t equals 0 because r of 0 equals your limit, your limit as t approaches 0 of r of t. Okay, and let's look at one more. So the continuity of a vector value function, example 6. Okay, so this one, determine the interval on which the vector value function is continuous. Our vector value function is r of t equals t squared of t plus 1 and t squared plus 1. Okay, so we're finding the interval on which this vector value function is continuous. Well, this component, if we want to call that the f of t, is continuous on all real numbers. This is only continuous when t plus 1 is greater than or equal to 0, or t must be greater than or equal to -1. This, if we want to call that h of t, that's continuous all real numbers. Okay, so you have to find what limits. If any component is not defined, then the whole vector value function is not defined. Okay, so for this problem, r of t is continuous on the interval from -1 to infinity. Okay, and that's all for now.